Okay, let's get started on an example here where we'd like to use the slope theorem and the first derivative test. Okay, to sketch a graph of the function f of x equals to absolute x times x squared minus 6x. Okay, so that's our problem. Okay, and then identify all of its extreme values. Okay, very good. So that's our problem. Okay, so we know that f of x, which equals the absolute value of x times x squared minus 6x, may be expanded as x times x squared minus 6x in case x is positive valued, right? The product, of course, would be 0 if x is 0, and it would be negative x times x squared minus 6x if x were negative. Okay, and so you could see that this would simplify to the formula x cubed, okay, minus 6x squared. If x is positive, it's 0. If x equals to 0, and it's 6x squared minus x cubed in case x were negative. And so therefore, the formula for f prime of x could be rewritten as so then the formula for f prime of x, so differentiating, okay, the x cubed minus 6x squared, we get 3x squared minus 12x, right? If x is positive, we would have differentiating this formula here, we would get 12x minus 3x squared if x were negative. Okay, and so we see that as x converges to 0 from the right side, f prime of x converges to 0, and as x tends to 0 from the left, f prime of x also approaches 0. So the derivative would be 0, in fact, if x equals to 0. And so we could simplify this formula to be 3x times x minus 4. That would be in case x is positive. Derivative is 0 again if x is 0. And it's 3x times 4 minus x if x were negative. Okay, and so what we see that the critical numbers, right? In other words, the numbers where f prime of x is exactly 0 occur if x is equal to 0 or x equals to 4, right? So these would be the two critical numbers for the function. Okay, and now if we'd like to examine where the function is increasing and decreasing, remember we use that slope theorem, right, where we said we use these critical numbers to split the x-axis into sub-intervals, and we check out, right, the sign of the first derivative on each interval, right? So we notice that with respect to f prime of x, right, it's defined to be 3x times x minus 4, when x is negative, okay, on this interval here. And clearly, for any negative x, 3 times x is negative, and x minus 4 is also negative. So we have, I'm sorry, 3x is negative. Sorry, because in this case, right, when x is negative, sorry, this should have been 4 minus x. So when x is negative, of course, 4 minus x would be positive. So we get a product of a negative with a positive number, which of course is negative. So that means the function f has a negative slope everywhere on the interval from minus infinity to 0, and therefore f is decreasing on the interval minus infinity 0. However, once x exceeds 0, the first derivative of f is given by the formula 3x times x minus 4. Okay, and so therefore we see that between 0 and 4, okay, 3x is now positive, and x minus 4 would be negative. So the product here, right, of a positive and a negative is a negative. So again, we still have negative slope for the derivative of f, and so therefore f is still decreasing on the interval from 0 to 4. Okay, and then finally, if we take the case where x exceeds 4, then 3x is a positive number, x minus 4 is a positive. So the product is positive, and therefore we have a positive slope, so f is increasing on the interval for infinity. Okay, so if we just figure out what happened, to the function f at the critical numbers 0 and 4, right? These being the two critical numbers, we see that f of 0, right, is going to be 0 times 0 or 0, and it's a point where we have neither a local maximum or minimum value. However, the slope is 0 there, right? So this is not a relative extreme value, but again, the slope is 0 because f prime of x is 0 at x equals 0. And at x equals to 4, the value of the function is going to be here 4 times 16 minus 24, right, minus 8. So the value of the function is negative 32, and we know that that value corresponds with, right, this is a relative minimum value, okay, the minus 32. Okay, and so now we could say, all right, so let's go ahead and, try to do a little plot of the function here. So here's our x-axis, and here's our y-axis, and so the critical numbers were at 0, where the function was 0, and it had 0 slope, and then say there's 2, 4, okay, 6. Then at 4, we had the relative minimum value of minus 32. Okay. So perhaps we come here, to our y, and y-axis, we're going to scale it differently. Say this represents negative 16. So here we'd be at a value of negative 32. And so, here it'd be positive 16, positive 32. So the points of interest again were at the origin, you know, where we had a zero slope, and then at the point x equals to 4, where we had a zero slope and its relative minimum value. Okay, and so therefore, you know, maybe we just you know, find some other interesting points on our graph. For instance, we could see that note also that an x-intercept, okay, in addition to x equaling 0, right, when we factor the x squared minus 6x, we would get x times x minus 6. So in addition to x equals 0, x equals 6 is a is one of the intercepts, right? F of 6 is equal to, you know, 6 times 36 minus 36 equals 0. So that implies, you know, yeah, that the x-intercepts for our graph are going to be at 0, 0 and at 6, 0. Okay, so we have that point, and maybe, you know, just to, okay, to get another point on the graph, say a point where we have a negative x value, say we just evaluate f, say, so here at, say, minus 2, and we could see that f evaluated at minus 2 would equal to, you know, the absolute value of minus 2 times minus 2 squared is 4 plus 12. So we would have 2 times 16, or positive 32. Okay, so another point on the graph of our function would be this point 2 comma 32. And so now we could simply look at what we know about the function f, and namely it's always decreasing, right, from minus infinity to 0, and it has a 0 slope, you know, at the origin. So it had to be decreasing something like that, and then it continues to decrease, right, from 0 to 4. However, you know, it's going to bottom out at x equals to 4. And maybe we just throw in another value of f. What's f's value, say, at positive 2, just to get a little more accuracy on our graph? Well, f of 2 is going to be 2 times 2 squared is 4 minus 12, or 2 times negative 8, right, which is, of course, negative 16. So at 2, we're at negative 16. And so, you know, you could see that the graph, right, to have a 0 slope here and to continue to decrease, it actually has to change its curvature at the origin from kind of curving up on the left side of the point to curving downward on the right side of the point. And then at some point between 0 and 4, it's going to change its curvature again and start curving upwards, okay, so that it can bottom out and round out at 4, because then, right, once we exceed 4, our function is always increasing, and it's going to pass through the x-axis again at x equals to 6. So this would be a rough graph of the function, and so we see that f of 4 is minus 32. This would be the relative and the absolute, okay, minimum value for our function f. Okay, and regarding absolute or relative maximums, well, you could see there is none, right? There certainly is no absolute maximum, because, you know, the range of the function is unbounded above, right? Goes up to plus infinity. So there's no absolute maximum, and actually, right, there's no relative maximum, right? There's no, you know, crust anywhere, right? And there's no high point, anywhere along the graph of the function. So this is just another example then of graphing a function that was slightly more complicated than the example we did in class Friday morning, because of the fact that it had this, right, it was almost polynomial, but it had this one factor of absolute x that made it slightly more complicated. So so this is just one more example to add to the list that we worked through in class on Friday.